Now let's see if we understand this principle. I have a simple circuit. It's hooked to a 12-volt battery. And if I ask you to rank the bulbs, you know that that top bulb is brighter than the other two. It's an indicator bulb getting all of the flow through the current, through the battery. The other two each get half. So the question is, what's the voltage across bulb A? Is it greater than 6, equal to 6, or less than 6 volts with your clicker? Which is it? Okay. Okay, most of us say greater than 6. Now some of us said equal to 6. The problem is, some of us are using a different model. Some of us are saying all the voltages of A, B, and C have to add up to 12. Some of us are saying just A and B have to add up to 12. Which is the correct model? Argue with your neighbor real quick. Which is the correct model? Okay. We all went up in the airplane. Did any one of us come down on both paths? No. We all either took the easy path down the ridge or the hard path down the cliff. We did not, any of us, take both. Likewise, if we take an electron, paint him green, call him Fred, Fred has to go through, well, first of all, the magical plane takes him to the top of the cliff. Fred has to go through A. He has to fall through that drop. But then he can either go through B or through C, but not both. So that means that the journey by Fred is either going to be A and B, and that's got to add up to the 12 volts, or it's going to be A and C, and that's going to add up to the 12 volts. So the correct answer is the one on the right is correct, the one on the left is garbage. Now, if this plus this has to add up to 12, and that's brighter than that bulb, what does that tell me about the volts across bulb A? Well, it's got to be bigger than half, bigger than 6. And so the correct answer is A. Okay? Now, here's another way of looking at it, another perspective. If we think of voltage as the battery's ability to push, the oomph, if you will, the oomph of the battery, there's only so much oomph, 12 volts. Now, that oomph has to be spent getting coulombs through boxes that are hard to get through, that are obstacles, resistance to the flow. Now I look for things that are in series. Is A in series with B? No or heck no? Heck no. What is A in series with? The network of B and C. Now that means that the battery has to get the same number of coulombs through this box containing A each second as it gets through this box containing B and C each second. The current has to be the same through both boxes because they're in series. Now, how does that oomph of the battery get divided up? Well, I find if I measure the voltage across the boxes that I get a bigger measurement across the top box. How do I know that? Well, that's a brighter bulb. Brighter bulb means more volts. Okay? Now, which of those boxes, the top one or the bottom one, is harder to get through?
Top one.
The top one. Two paths in parallel are twice as easy as a single path, and so that means the greatest resistance is the top one. Now, here's the idea. For series networks, and this is only true for series, only true for series, the voltage drop is greater across the larger resistance. Now think, if you will, about a simple circuit. Oh, I did not write that. I have been betrayed by my brothers. I will speak with them. Okay. If I have 3 identical bulbs in a series circuit, and it's a 12-volt battery, they're all going to be equally dim, are they not? And that means that they're each going to have the same voltage drop across them, and that voltage has to add up to 12. So that's going to be 4 volts, 4 volts, 4 volts. Now if I were to arbitrarily put these two in a box, box A, and I put this one in a box, box B, I would say that box A has twice the resistance of box B, would I not? And if I measure the voltage across box A, what would I get? From here to here, 8 volts in the circuit, and 1/3 of the battery's oomph is dedicated to get coulombs through it. Check that your neighbor's on the bus. Okay. This is where it gets good. This is where I show you how to solve the pizza problems. We could not compare B versus D, because B got all of the small, D got more than half of the large. Let's use voltage. If that's a 12-volt battery, A and B are in series. They're going to be just as bright as each other, and so that means they have to be 6 volts and 6 volts. It's got to add up to 12, and they're just as bright as each other. Now, with the current model, you decided that C had to be brighter than A. That it was the indicator for the easy branch, and A was the indicator for the hard branch. Now, if C is brighter than A, it's got to have more volts across it than A. That's got to be bigger than 6. Now, I'm going to put a number to that. 8. I made that up. I pulled it out of my right ear. Okay? If that's 8 volts, what's that? 4. And what's it across this bulb? 2. And 2. Every path has to add up to 12. That would be 8 plus 4 is 12. 8 plus 2 plus 2 is 12. Now folks, what I just did is a dangerous thing to do. Because my model doesn't say it is 8. My right ear said it was 8. And I don't always believe it. Okay? I made that number up. Sometimes when you make numbers up, you can convince yourself of wrong physics. All we know for sure with this model of ours is it's got to be bigger than 6. And that means that D has to be less than 6 volts. If I'm comparing 6 volts to less than 6 volts, that's easy enough. Okay? B is going to be brighter. Now, the way we would argue that on an exam is I would choose a path that went through B. From one side of the battery to the other. And then I would find a path that went through D from one side of the battery to the other. Since both of these paths have to add up to the 12 volts of the battery, they have to be equal to each other. Now if I am trying to compare B versus D, the first thing I have to do is compare A versus C. If I know that C is brighter than A, then the inequality goes that way. If I compare B and D, I mean this has to be equal. So if the inequality is going this way for this pair, it's got to go the other way for the other pair.